You ever see those Roman numerals tucked into chemical names like iron 2 chloride and wonder what they're all about? Well, they're not just there for decoration. In chemistry, a name is a precise code, and today we're going to crack a really important part of it.
So, picture this. You're in a lab and you need iron chloride. You look on the shelf and you find two different bottles. They both say iron chloride. They're both made of the exact same two elements, iron and chlorine, but they're clearly not the same thing. So, what's the deal? How do we tell them apart? This isn't just a fun little puzzle. In chemistry, mixing these up could be a huge mistake. And here's what's really going on inside those two bottles. One is FeCl2, meaning one iron atom for every two chlorine atoms. The other one is FeCl3, that's one iron for every three chlorines. They have different structures, so they've got to have different names. The question is, what are those names?
Well, the key to solving this whole naming mess is a kind of hidden number. It's called the oxidation number, and it's the secret piece of information that's going to unlock the correct name for each of those bottles.
So, what exactly is an oxidation number? You can think of it as a value that we assign to an atom that tells us about its charge inside a compound. It can be positive, it can be negative, or it can be zero. For our puzzle, understanding this little number is pretty much everything.
Now, don't worry, we don't need a whole textbook of rules to figure this out. For our iron chloride problem, we just need two simple things. First, in a neutral compound like ours, all those individual oxidation numbers have to add up to zero. The whole thing has to be perfectly balanced. And second, for this puzzle, we just need to know that each chlorine atom has an oxidation number of -1. That's it. With just these two rules, we are ready to go.
All right, with those rules in our back pocket, it's time to do a little detective work. Let's figure out that hidden number for the iron atom in each of our compounds.
Okay, let's start with the first one, FeCl2. We've got two chlorine atoms, and we know each one is -1. So 2 times -1 gives us a total charge of -2 from the chlorines. Now, since the whole compound has to balance out to 0, what does that single iron atom have to be to cancel out that -2?
Yep, you got it. +2. That's our answer. The oxidation number for iron in this first compound is +2. Let's hang on to that number and see what we get for the second one. Now for the other bottle, FeCl3, we're going to use the exact same logic. This time we have 3 chlorine atoms, each with a charge of -1. So that gives us a total of -3. Again, for the whole thing to be neutral, what does that one iron atom need to be to balance out a -3? +3. Perfect. So the iron in our second compound has an oxidation number of +3. And there we go. Our two hidden numbers are +2 and +3. Now we can finally give these compounds their proper, unique names. And this is the moment where it all clicks. All that math was to find these two little numbers, because chemists came up with a brilliantly simple way to put that number right into the name. And here it is, the big reveal. For FeCl2, where iron's oxidation number was +2, the name is iron 2 chloride. For FeCl3, where iron was +3, the name is iron 3 chloride. That Roman numeral isn't some strange code. It is the oxidation number. It's that straightforward. And this really gets to the heart of why this whole system exists. It's designed, as our source material says, specifically to distinguish different compounds made of the same elements. It just gets rid of any possible confusion, which is absolutely essential for clear and safe science. So look, if you remember just one thing from all this, make it this. The Roman numeral you see in a chemical name is literally telling you the oxidation number of the element that comes right before it. It's not just a random label, it's a crucial piece of data hiding in plain sight. Now you might be thinking this is just a special rule for metals like iron, but what if I told you this naming code is way more common than that? Let's check out another example, this time with a nonmetal. Take a look at these different oxides of nitrogen. Using the same rules, where oxygen is usually -2, we can figure out the oxidation number for nitrogen in each one. For N2O, nitrogen turns out to be +1, so we call it nitrogen I oxide. For NO, nitrogen is +2, which makes it nitrogen 2 oxide. See? It's the exact same system. It's a really powerful and consistent code. Okay, so we've gone from the formula to the name, but the real test of whether you've got it is, can we work backwards? Let's see if we can build a chemical formula just from its name.
Let's tackle this one, sodium chlorate V. Right away, your eyes should go to that Roman numeral. That V is our biggest clue. It's telling us loud and clear that the oxidation number of the element right before it, chlorine, is +5.
Okay, let's walk through this step by step. We know a couple of things just from basic chemistry. Sodium is pretty much always +1, and oxygen in this kind of compound is -2. The name just gave us our third piece of the puzzle. Chlorine is +5. Now, since the whole compound has to be neutral, if the sodium is +1, then the rest of it, the chlorate part, has to add up to -1 to balance it all out. So our little math problem is +5 from the chlorine plus some number of -2 oxygens has to equal -1. A little bit of algebra and you'll find that N, the number of oxygen atoms, has to be 3. And there it is, 1 sodium, 1 chlorine, and 3 oxygens. The formula for sodium chloride V is NaClO3. We did it! We successfully used the name, including that Roman numeral, to build the correct chemical formula from scratch.
So, it turns out those Roman numerals are so much more than decoration. They're a core part of the language of chemistry. They're a direct message telling you the exact state of an element, so we can tell two very different compounds apart. You've basically cracked the chemical code. Now, what other names out there can you decipher?